All right, today we are talking about the 5% approximation in ice tables, which is something that I alluded to last week. I said that this week we will be learning how to use the 5% approximation, and if you've watched any of the math skills for chemistry videos that I have up there posted online, there are videos that allude to the fact when we can use the 5% approximation and when we can't. So we're going to talk about the 5% approximation today and talk about when we can use it and when we're not allowed to use it. But it is a great tool for us, and I think you're really gonna like it. So what does it mean to be reactive favored? Well, this is why I said you have to know how to interpret K, right? K is super crucial here because we need to know how to interpret it. If K is less than 1, that means that we are reactive favored, right? Because remember, K is calculated as products over reactants. To get a value of K less than 1, that means that what? The denominator is bigger than the numerator, right? In other words, reactant concentration was bigger than product concentration. So that means that you have mostly reactants at equilibrium, right? You have very little product present if K is less than 1. Now the opposite is true if K is greater than 1. How do you get a value of K greater than 1? That means the numerator, the products, is bigger than the denominator. So for instance, 4 over 2 would be greater than 1. 2 over 4 would be less than 1. So let's look at this reaction, just a generic reaction. A is in equilibrium with B plus C. All three of them are aqueous. And we're told that K is equal to 4.3 times 10 to the negative 5th. Okay, that's reactive favored, right? This is definitely a value less than 1. So last week, we learned how to do ice tables, just regular old ice tables. We didn't know anything about the 5% approximation. This is what we would have written, right? We would have said initial concentration, 0.975, 0, and 0. And this would go down by x, this would go up by x, this would go up by x. So at equilibrium, we have 0.975 minus x, quantity, and then we have x, and then we have x, right? We're just assuming we're beginning with a 0.975 molar concentration here. We don't know anything about the products. So how did we do this last week? This is the method that we used last week. Right? We said, okay, if it's a 0.975 molar initial concentration, 0, 0, this is going to be 0.975 minus x, this is going to be x, this is going to be x. Right? So what's my equilibrium expression? K is equal to concentration of B times concentration of C over concentration of A. Right? That's the equilibrium expression. Now I plug in my values. X times x gives me x squared. 0.975 minus x goes right here. And then we're setting that equal to K, right? So now we have to solve for x and then plug it back into my ice table, just like we did last week. So we've got to do some rearranging, dreaded rearranging. That's going to produce the quadratic equation because to get this numerator and to get this denominator to go away, I multiply both sides by 0.975 minus x, 0.975 minus x. Okay, so that's what I get here. So now I distribute this times this times this, equals x squared, and then I rearrange it into a format that I'm familiar with, because to plug into the quadratic equation, right, we want to have a x squared plus bx plus c equals 0, right? So now we're plugging this into the quadratic equation, negative b plus or minus square root of b squared minus 4ac all over 2a. Whew, we crunch some numbers. We're using a is equal to 1, B is equal to 4.3 times 10 to the negative 5th, and C is equal to negative 4.19 times 10 to the negative 5th. So I did not put that on the slide. I'm assuming you can do the quadratic equation by now. It's just tedious, right? It's not hard, it's just tedious. And the quadratic equation will always give us two roots. We get x equals negative 6.49 times 10 to the negative 3rd, x equals 6.45 times 10 to the negative 3rd. How do I pick the answer that works? Well, if I plug x in right here, which is what I'd be doing, right? I'm not subtracting it from anything. I'm not adding it to anything. I'm just taking x and plugging it in straight. Obviously, I can't plug in a negative here. I can't have a negative concentration. That's nonsense. So this negative root is out. This is my answer that I get, right? So I plug that in. I just expanded it because this is 6.45 times 10 to the negative 3rd. 1, 2, 3. 6.45 times 10 to the negative 3rd. Okay? Plugging in x right here, 0.975 minus 0.00645. Now rounding my final answer to 3 sig figs, I get 0.974. So now my question for you is, did the concentration of A change significantly? right? This is clearly reactive favor because my concentration of products is very small, right? 0.00645 molar. That's a small concentration compared to this. So my question is, did A concentration actually change all that significantly? Because look, this is the tenths, this is the hundredths, this is the thousandths place. So to get any change, you have to go out to the thousandths place. Is that a significant change? Well, let's look at something. It's called the 5% approximation. We are going to use this only in a reactive favor condition. Okay, if K is less than 1, K must be less than 1. Put that big star in your notes. Okay, K must be less than 1. K is greater than 1, we cannot use this approximation. K less than 1. Then we're assuming that at equilibrium, the initial concentration of the reactants basically equals the initial equilibrium concentration of the reactants. In other words, we're assuming no change going from I to E, right, which is what I just said. We assume reactants doesn't change substantially. If you look at our previous problem, to see a change, we had to go to the thousandths place. So we're assuming, using the 5% rule, that the concentration of those reactants isn't changing significantly. So we're going to plug in the initial value as the equilibrium value, and then do the math that way. See what that gets us. So let's do that same first problem again, but this time we're going to use the 5% approximation, see what you get. So if we use the 5% approximation, that means we're taking this value and we're just dumping it right here. Okay, this is still 0 plus x, this is still 0 plus x. So ignore this line right now, okay, because I'm kind of showing you the answers before we do the arithmetic. This is what your ice table would originally look like. Right, now we write our equilibrium expression, K is equal to B times C over A. Right, now instead of plugging in 0.975 minus x, we're just plugging in 0.975, okay? Make sure you understand what we did. We're taking this initial value and putting it in right here. We're saying, in other words, this and this are the same. And now, when we solve our arithmetic, what do we get? No quadratic, woohoo! Because to get this to solve, right, multiply both sides by the denominator, 0.975, 0.975, that's what we do here. Now we say to ourselves, okay, x squared is equal to 4.19 times 10 to the negative fifth. How do I get rid of something that's squared? Just take the square root. No quadratic equation. Yay! Right? This is why I think you'll really like the 5% approximation, because it eliminates the need for the quadratic equation. So let's compare our answers. Was it appropriate to use the 5% approximation? Yes or no? So here's the ice table we got using the quadratic equation without the 5% approximation. 0.974, 0.00645, 0.00645. Here's what we got with the approximation. 0.975, 0.00647, 0.00647. Okay, so just by looking at it, you can't decide, because some people could be really, really scrupulous and say, hey, this going up from 0.00645 to 0.00647, hey, that's significant to me, right? You need to have a standardized way to know if this difference is meaningful or not. And so how do we check our work? The way we're going to do that is we're going to figure out what 5% of our initial concentration is. And that'll produce a range of answers that we can accept. So the range of answers that we can accept is the initial concentration plus or minus 5%. And then if the answer you get using the approximation falls into that range, then we're good. We're cool. We don't have to do anything. So let's look at our two answers. Here are my two ice tables. Okay. So my initial concentration was 0.975, right? 5%, convert percent to a decimal, right? So moving 2 to the left, 1, 2. So 5% is equal to 0.05, yes? And so that means 5% of 0.975 would just be 0.05 times 0.975. You with me? So that gives us a value of 0.04875. We'll round to sig figs later. So what does that mean? What's our acceptable answers range? Well, it's the initial concentration plus or minus 5%. So here's the minus and here's the plus, right? So that gives us a range of 0.926 to 1.02. Now let me ask you a question. This is just a question that you need to ask yourself to make sure you're talking yourself through the logic correctly. Would it be possible for this to go up? Would it be possible for it to go up? No, it wouldn't, right? Because where would this come from? Well, this is 0, this is 0. So obviously, it's not going to go up. But you want to get in the habit of looking at both the plus and the minus, because if these two values were not 0, if this, say, was let's say this was 0.33333333, okay, then it is possible that A could go up. But because B and C are both 0, then obviously it doesn't make sense that A could go up. However, get in the habit of considering both the positive and the negative. It could go up, it could go down, depending on if you know the initial concentrations over here or if you don't. If you don't, then obviously it's not going to go up. So anyway, that's our range, right? And so when we plug our value in, we plug in our value, we got an answer that falls within that range. So that means we're okay, right? We get our value of X, we plug it in, and we look at where does it go. Now that's not 0.974. Is it? Let's see. It doesn't look right. 0.975 minus our value of X, 6.47 e to the minus third. That's 0.968. That's a typo. Okay, so what we do is we take the value of X that we obtained using the approximation, plug it in, and that's where we get our answer. Okay, that's how we got this 0.968. Does that make sense? Okay, 0.968 is coming from the value that we got for X, plugging it in as if we were not making the approximation and seeing what we get. We get 0.968 if we plug it back in. That's where that number comes from. 0.968 is within this range, so that means that we can use these values of X and not worry about it. We're good. So this is really important. Please write this in your notes. When can I use the 5% approximation and when can I not? I can only use the 5% approximation for a reactant favored ice table, and K must be less than 1. And when can I not use the 5% approximation? If it's product favored. In other words, if K is greater than 1, can't use this approximation because this assumption is that A is not changing. Well, if it's product favored, then A is going to change a lot. So that's why I can't use it if it's product favored. All right, so here's one for you to try. You're just considering a generic reaction, X in equilibrium with Y and Z. Let's assume they're all aqueous, and there's the value of K. You begin with a 1 molar solution of X. What are the concentrations of Y and Z at equilibrium? I'll pause the video and give you a chance to try this. All right, let's go over this problem. So we're told that it's a 1 molar solution of X that we begin with. What are the concentrations of Y and Z? All right, so because K is significantly less than 1, we're going to make the 5% approximation here, right? Because 1, 0, 0, this is going to go up by X, this is going to go down by X. We're going to assume that 1 minus X is approximately 1. Okay, X is small enough that it's not going to change significantly at equilibrium. So that's what your ice table should look like if you're making the 5% approximation. Now we're going to do the math, right? K is equal to Z times Y over X, yes? So X and X go right there, and 1 goes right there. Okay, so we do some rearranging, multiply by 1, multiply by 1. X squared is equal to 2.49 times 10 to the negative 4th. So how do I get rid of something that's being squared? I just take the square root, right? Dividing by 1, that's not going to change the number any. So I take the square root, and I get 0.00249. Double check my math just to be sure. 2.49 e to the negative 4th square root. Ooh, yeah, that is a typo. Because that didn't look right. 2.49 e to the negative fourth square root. Yep, that's 0.0. It's a typo. 0.158. .0. Oops. Okay, sorry about that. Typos happen, right? That just happened. I made a boo-boo there. When I took the square root of that, I just copied and pasted and didn't do actually the changing, so my bad. So there's my value of x, right? Just take the square root of that. Okay, so what's 5% of 1? That's just 0.05, right? 5% is 0.05. 0.05 times 1 is 0.05. So that means that our answer, when I plug x back in, needs to fall in the range of 1 minus 0.05 to 1 plus 0.05. Again, is it going to go up? Could it be possible for x to go up? No, right? Because these two values are 0. So law of conservation of mass says, hey, x can't go up. But in the future, if y was, say, some value greater than 0, it could be possible. That's why we always want to consider both the positive and the negatives to just get in that habit. Okay, so my range of acceptable answers will be 1 minus 0.05 to 1 plus 0.05. So it's got to fall in the range of 0.95 to 1.05 when I plug x back in. So I got x of 0.0158. Plug that back in. When I plug that back in, I get 0.984. Okay, is 0.984 in that range? The answer is yes. Okay, so because this answer falls into this range, then I'm okay to keep this value of x as my final answer. So if I asked you on a test, what's the concentration of y? You would say 0.0158. Okay, you just plug it in directly. And then you would just keep that as 1. So x would be 0.0158. Okay, and you're good to go. Hope we're all cool on this one, because here's another one for you to try. I'll pause the video. Let's look at the answer to this problem. What are the equilibrium concentrations of all species when we begin with a 0.65 molar? And you don't need to worry about the name of that acid. Now here's the trap laying in wait for you here. What is it? There's a liquid, right? Liquids don't participate in equilibrium. So our ice table had better not include water, right? That's the solvent. And this is reactive favored, so we can't make the 5% approximation, right? We're omitting the water because it's a liquid, and we're making the 5% approximation. So this initially is 0, this initially is 0, this is 0.65. This is going to go down by x, these are going to go up by x, that gives me x, and 0.65, right? Because I'm making the 5% approximation since k is less than 1. Now when I do the math, I say to myself, okay, x squared over 0.65 is equal to 1.36 times 10 to the negative third, because that was my value of k. So when I get x, it's 2.9 times 10 to the negative 2. I think I wrote 3 here. Sig figs. Sig figs are what got me there. So when I plug x in here, 0.65 minus x, that gives me 0.621. Okay, is 0.621 in my range of acceptable answers? Well, what is my range of acceptable answers? 5% of 0.65 is this value. So that means that my range is 0.617 to 0.683. 0.621 is in that range, so I'm good. And so that difference here is just a sig figs rounding thing there. Okay, that's just sig figs and rounding. All right. I have a glitch here. Hang on a second. All right, somehow my slides got out of order. So here's the last problem for you to try. P is in equilibrium with Q and R. All three are aqueous. There's your value of K. You begin by placing 1.5 moles of P in a 2-liter container. What are the equilibrium concentrations of all substances? I'll give you a second to try that. All right. So here's the question for you. Can you use the 5% approximation here? The answer is no way. Why? Because K is 120. Is that reactive favored? No, not at all, not even slightly, right? If K has got a value of 120, that means that I cannot assume that the concentration of P is not going to change very much during the course of this equilibrium. I'm going to assume that it's going to change a lot, because now that means it's product favored. That means that these concentrations are going to go up a lot. That means this is going to go down pretty significantly. So the trick here is that you can't make the 5% approximation. You've got to do this the long way. Always look at your value of K before you decide if you're making the 5% approximation or not. Because if your K is greater than 1, you can't do that, not allowed, okay? Now we've also got to watch out for another trick that I've got laying in wait here for you, right? You can't plug in 1.5, problem says it's 1.5, right? That's just number of moles. You have to convert that to molarity. Moles over liters gives me molarity. So it was a 1.5 moles in a 2-liter flask. That's why it's 0.75. All right, so now we have to do this the long way. Sorry, guys, right? This is why you have to watch. You have to watch, have to watch, have to watch. K is greater than 1, so that means that I have to solve the quadratic equation. When I get a value, I get a negative root, which obviously is not going to make sense. And then I get a positive root, right? Because I can't have a negative concentration of Q, negative concentration of R. That makes no sense. So I get a value of 0.745. Well, look what happens here. 0.75 is my initial. 0.745 is how much it changed by. So yeah, P changed a lot. This is product favored. That means that the amount of P went way, 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 way down. That means that the amount of concentration, the concentration of the two products went way up. Okay, so that's the difference between a reactant favored and a product favored. Reactant favored, we can make the 5% approximation, and so long as our answer, when we plug X back in, falls in that range, we're good. We can assume that the value of X is going to hold up. It was okay to make that assumption. But if it's product favored, we cannot make the 5% approximation. Can't do it, because the 5% approximation assumes that the concentration of the reactant isn't changing. Well, obviously, if it's product favored, the concentration of the reactant is changing a lot. How can you have lots of product if the reactant concentration doesn't change? Doesn't make sense according to the law of conservation of mass. Okay, so please make sure you understand when you're okay to use the 5% approximation and when you're not. All right, so that's where we're going to stop for today. And when I next see you, we'll be doing some enrichment on this stuff.